All right, welcome back to another problem session where we are going to work on equilibrium problems. So, equilibrium, as you know, is a condition that certain reactions meet, and equilibrium is expressed to us as a double-headed arrow that we see here. And so, I've got a few problems that I want to work out here for y'all, and so the bulk of the work has been done already. So the first one here is we're taking a reaction and we're given specific information. So it says at 300 degrees Celsius, the equilibrium constant for the reaction is 11.5. Concentrations of PCl3 and Cl2 at equilibrium are both 0.0100 molar. Now, what's important to understand here is that it tells you at equilibrium, and so that gives us information that we need to use in order to solve for the equilibrium concentration of PCl5. So what I've done is I've set up the ice chart, and this is not necessary, but I do it just because I want to see where all the different parts are at. So for PCl3 and Cl2, we're given the equilibrium concentration, so none of this other information is important. And really, we're not needing the ice chart, but I do it again just because I want to see what the stoichiometry is. Because in the end, the stoichiometry was what's important here. Now, we take the information that we're given, we write the equilibrium expression that you see here, where you have products of reactants, so PCl3 times CO2 divided by PCl5. And now taking the information they give us about the equilibrium concentration being 0.01 molar, we put that information into for PCl3 and Cl2. Now the PCl5, and that's going back to my ice chart here, I see that it's only 1 to 1 to 1 stoichiometry, so that makes it easier. So therefore, we're just going to put X in place there for that. We don't know what the initial concentration is, so we can't put that in. And it's not important because we're going to use the equilibrium concentration to solve for X here. So we put that in. Now we solve for X here. We go through just a little rearrangement. This is squared, and we end up with 8.7 times 10 to the minus 6. Now, if we did this correctly, if we take this 8.7 times 10 to the minus 6 and we plug it into your X value here, when we go through the math, we can calculate the value of case of C. Now, the value of case of C should be consistent with what the actual value is, which is 11.5. So you always can check yourself to make sure that your algebra is done correctly. In our case, it has been done. So I'll just put a little check mark there showing that I did that. And so since it's just a simple 1-to-1 ratio, it's all x's, so x is equal to 8.7 times 10 minus 6. That is the equilibrium concentration for PCl5. So very quick and simple there. The main thing here to understand is that you're given equilibrium concentrations for two different species, and knowing that information, we can go back and recalculate the value for x, which in turn is the concentration for PCl5. So you don't always have to work with initial concentrations. This problem, you're given equilibrium concentration, so it makes the problem a little bit easier because you're not having to actually solve for X like you normally would with the ice chart. So now in problem 2, we're given a mixture of sulfur dioxide, oxygen gas, and sulfur trioxide. They are given concentrations. Is the reaction equilibrium? If not, which way will the reaction proceed to reach equilibrium? So in this particular problem, what we need to do is we're going to set up the equilibrium expression based off the products of reactants. And you can notice that this one's not a 1-to-1. This is a 2-to-1 to 2 ratio. So we have to make sure that we input the correct exponents for each of those reactants and products. Now, We know our K is given to us. What we're going to do is solve for Q. We're going to solve for the reaction quotient. And we input the information given to us here into the expression for Q, and we solve that to be equal to 5.01. Now, if we compare Q to K, what we notice is that Q is much smaller than K, meaning that your reactants are much larger in concentration. So naturally, if your reactants are higher, the equilibrium is going to shift towards the products. And so the answer to the question is it's not at equilibrium because they're not equal to each other. Q and K are not the same value. So it's going to shift towards the products to establish equilibrium. The third problem we're going to look at is involving yet again another equilibrium problem. Now this one we're taking the reaction given to you here, and it's asking you, given the initial concentration of CH2Cl2 is 0.0206 molar, we're going to fill the information into the ice chart. So they give you the initial concentration, so we plug that in here. They give you nothing, so those are going to be 0. Now the equilibrium is going to shift towards the product, so these are going to go up, or this is going to go down. Now pay attention to the fact that this is minus 2x because you have the coefficient 2 here. So we put them together, 0.026 minus 2x, x and x. So once we have our ice chart, what we can then do, we can write the equilibrium expression, and we can include what's from the ice chart into the expression and solve for x. So I plugged in x times x divided by 0.0206 minus 2x squared. And again, the square comes from the fact that you have the 2 in the coefficient here. And so x times x is really x squared. So to simplify this, we're going to take the square root of this fraction. And so you also have to take the square root of the other side. And that gives you this setup here, okay? So we are going to now get x by itself so we can solve for it. We're going to multiply this over here and distribute through the parentheses. I show that here. And then we're going to subtract, actually we're going to add out the 2.04x to the other side. So we have 3.04x is equal to 0.021. So we're going to divide out the 3.04 and you get your x to be equal to 0.0069. Now the next thing we're going to do is we're going to check ourselves. And so you take the value for x, plug it back in to the expression up here. All right, and then recalculate it. Now I ended up calculating 1.029. The equilibrium constant for this is 1.05, so that's fine. All right, it's close enough to where it's good, checks out. So then I can say, okay, we're trying to calculate the equilibrium concentration of CH4. So CH4 is x is 0.069. So that would be the equilibrium concentration for this species. So this would be your answer. All right. Now, one of the things that you want to do in each of these equilibrium problems is you have to write out the equilibrium expression. Always remember that your equilibrium expression is going to be products over reactants, and your coefficients from the balanced equation are then going to be put into your exponents. You don't want to forget the stoichiometry for the expression, nor the ice chart. That's a very common mistake that we make. So I hope this is beneficial, and if you have any questions, you know what to do. Thanks.